This week we're going to be talking about oscillations, and this is a way of describing periodic motion. And this shows up a lot in physics, whether we're talking about, imagine an object that's oscillating because it's hanging from a spring, or if it's swinging in a pendulum, or when we start to talk about light or other types of oscillations, shows up in physics all the time. So let's very quickly talk about how we describe oscillating motion, and then we're going to look at a couple of examples of how this works. So if you imagine, let's say, a spring with a weight hanging off of it, I can pull this spring down, and when I release it, it's just going to go back and forth like that. And that back and forth motion is called the displacement of the spring, right? And it's going to bob back and forth. And I can draw that displacement on a graph. So if you imagine when it's down below the point where we released it, or where we hung it, it's negative, and if it's above it, it's positive. It started at, we pulled it down, so let's say it started at this point. We're going to wind up getting a wave that looks like that. It's basically going to look like a sine wave. And that wave we can describe its properties with things like wavelength. We'll call that lambda, so that's the wavelength. And the amplitude of the wave. So we have the amplitude and the wavelength. The wavelength is a measure of how far these crests are apart. There's also something called the frequency, f, and that's basically a measure of how many times one of these crests goes by per second. So if I was standing there watching this wave go by, I could count how many waves were going by every second, and that would give me the frequency. So the frequency is measured per second, and we call that a hertz. So it's 1 per second, and that's a hertz, Hz. And we can describe this entire wave as something with a given amplitude, so that's our amplitude A, times the cosine of omega t plus some phase constant. And the phase constant just shifts this wave back and forth. Now this is the angular frequency, and there's a relationship between the frequency and angular frequency. The angular frequency is 2 pi times the frequency. So this is in radians per second. This is just in per seconds. So it's basically saying, since we're in a cosine function, we need to have units for that, so that this gives us a proper value. So this 2 pi just goes in. Think about the 2 pi as once every cycle. Right? Another aspect of this is the period. We'll call that t. That's the period. So that's how long we go. How long does it take to go from one crest to one crest? And that is basically related to the angular frequency as 2 pi over the angular frequency, or 1 over the frequency. And so there's a relationship between the frequency of the wave and the period of the wave. Now the frequency of different systems depends on the properties of the system. For example, when it comes to a spring, the frequency is proportional to the square root of something called the spring constant divided by the mass. And the spring constant is the strength of this spring in units of newtons per meter. And that spring constant comes from a model of the force. If we imagine the force to pull that down, we get minus kx, where x is the displacement and k is the strength. And so that gives us an idea of the strength of the spring, how much that force is restoring the motion of the weight that's hauling it down. So this angular frequency is related to that. So if I increase the mass, that's going to cause the angular frequency to decrease, and if I increase the strength of the spring, it's going to cause it to increase.